It is part 2 of section 6.1. Here we'll study orthogonal vectors. Two vectors U and V in Rn are orthogonal if their dot product is 0. Here is the Pythagorean theorem. Two vectors U and V are orthogonal if and only if this equation is satisfied. It can be interpreted geometrically here for in two-dimensional coordinate system. Here that is a vector u, and v is another vector. Then u plus v must be that one. That is u plus v. You learned the right triangle, and this side, usually we are using notation a, b, and c. Now, so that a squared plus b squared is the same as c squared when this triangle is a right triangle. So that is the Pythagorean theorem. That is exactly this one. And also, algebraically, we can prove that u plus v norm squared is same as u plus v dot product with itself. And if we expand, then we have u norm squared, v norm squared, and 2 u dot v summation. Now, this one is the same as this summation if and only if this term is 0. That means that u and v are orthogonal. So algebraically, we can prove this one quite easily. Orthogonal complement. W is a subspace of Rn. A vector z in Rn is orthogonal to W if z dot W is 0 for all choice W from the subspace. A vector has dot product 0 with every vector in W. Then we say that the vector z is orthogonal to the space. Now we consider the set of all vectors that are orthogonal to W, and we call it orthogonal complement of W. And we are using the notation W perp or W perpendicular. Here in set notation, we define W perp in this way. That is the collection of vectors z, and with this property z dot W is 0 for every choice of W from the subspace W. Okay, let's see this example. W is the plane passing through the origin in R3, and L is the line and passing through the origin and perpendicular. That is a normal direction of the plane. Then if we choose any vector W from the plane and any vector z from the line, and we get the dot product, then must be 0 because it's always geometrically perpendicular. So L is just the collection of vectors orthogonal to W, and now W, the space, is collection of vectors orthogonal to the line. So we may say that here L is W perp and W is L perp. So once as a subspace, and if you try to get W pub, then W and W pub are completely independent. So we see here this example. W is a subspace of Rn, and prove that if X is in W and simultaneously in W pub, then the vector X must be 0. We can prove this one quite easily. Okay, hint is given here. Now, we start with X is in W, but it's also in W pub. But this implies that X dot W is 0 for every choice of W inside the subspace. Now, X is in W, so among this W, we may choose W is X, because X is inside here. So we choose W is the same as X. Then here this equation becomes X dot X equals 0. This implies that X is 0. So once X is in both W and W pub, then there must be 0 vector. This implies that a space and its pub are completely different, and only the shared vector is the 0 vector. Except 0, everything else are completely independent. Okay, here W is a subspace of Rn, and now let's say the dimension of W is M, which is less than or equal to n. Now consider a basis for W, and A is the collection of basis vectors, and then A must be in R n by m. There are m rows because each vector, the basis vector is in Rn, but there are only, basis should have only m vectors, because we say that dimension of W is m, and W must be column space of A. Just each column of A is basis vectors, so that their linear combination will produce every vector in W. Now we consider W pub. Then, okay, W pub is collection of vectors. Okay, now we start with here basis for W. Now that is collected as a matrix A, so that now A has such columns. Now once we choose a vector from W pub, then W and each column dot product must be 0. That is the same as that. Now if we consider A transpose, then this column will change into rows, right? So that, and rows of A transpose and W dot product is 0. It's the same as now column and W dot product is 0, right? But now this can be written as A transpose W is 0. So that we can say that W pub is collection of vectors X in Rn such that A transpose X equals 0 from this one. We can say that. Now, but this set is the same as null space of A transpose. Here A transpose is in R n by n, m is less than or equal to n from here. And now we can go further here. M is dimension of W. We set it here. And W is the same as column space of A. A is the collection of basis vectors of W. So we have here. Now column space, the dimension is same as column space of A dimension is the same as the column space of A transpose. So we reach it here. Now these two will be used for the following example. Let's see part B. A vector x in W pop, then if and only if x is orthogonal to every vector in a spanning set of W. Okay, this left-hand side is the same as that xn, okay, xn W dot is 0 for every choice of W from capital W. That is definition. Now, rather than every vector in W, if W has a spanning set, then now every vector in spanning set, for example, x dot and some u equals 0, and here every u in, okay, that is a spanning set. Just to say that spanning set, okay, there is more n, and set of W. Okay, now the vectors in W will be made as a linear combination of these vectors in spanning set, so that once it is true, then that must be true, and if this is true, then that must be true, so that here they are equivalent. So rather than every choice of vector from W, we may consider a spanning set of W, so that if x is orthogonal to the spanning set, then we can say here x is in the W pop. A basis is also a spanning set. Now we already used it in part A. W pop is a subspace of Rn. You can prove this one quite easily. If you choose any two vectors in W pop, then their linear combination is also in the set. So it is closed on the linear combination. So it is a subspace of Rn. W is a subspace of Rn. Prove that this equation. Now, from here, the dimension of W is the same as dimension of column space of A transpose. That is, so that it is okay, this one is the same as rank of A transpose, right? So dimension of column space of a matrix is rank of the matrix. Now for this one, now already W pop is the same as null space of A transpose. So dimension of null space of A transpose is nullity. So for matrix, and rank and nullity summation is the same as the number of columns of the matrix. So A transpose has n columns, so this summation must be n. That is the rank theorem, right? Okay, so we prove that. A is on n by n matrix, then the row space is the set of all linear combinations of the rows of A, and we use the notation row A. That means here, row space of A is column space of A transpose. Of course, row space is also subspace, because from the beginning, row space is a collection of linear combinations, so that if you choose two vectors from row space of A, then you can easily see that their linear combination is inside of the set, so that it is closed on the linear combination. So it is a subspace. Okay. A is an n by n matrix, the orthogonal complement of the row space of A. Here, orthogonal complement of row space of A is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. Once you read this sentence, then it's not easy to understand. Now, let's see some detail. Okay, for that one, here, once a vector V is in this space, then that means that along with row, okay, every row is row space A is spanned by rows of A, right? So that this is a spanning set of rows, okay, so that now row of A and rows of A are a spanning set, so that V is now row A per. That means that row dot here V must be 0. But this is exactly the same as now A, V equals 0. Once V is here, then equivalently now V is in null space of A. Similarly, you can check this one quite easily. Okay? Okay, now we have true or false problems. For any scalar C, U dot CV is C U dot V. Is it true? Yeah, it must be true. This is a basic property of the dot product. C can be multiplied to one vector, or after dot product you can multiply C, or you can multiply C to the other vector. So CU and dot product and V. So these three quantities must be the same. So it is true. If the distance from U and V equals to the distance from U to minus V, then U and V are orthogonal. Okay. For this one, it is true, and we can explain this one geometrically. Okay, that is now U vector, and this happens only when this case, okay, only at this case, there's V, and negative V, this is the origin, and negative V will be that one. So distance from U and V and distance from U and minus V must be same when this is orthogonal. If not, then V is here, and now negative V is here, and then this distance, that distance must be different, right? So geometrically quite easy. Now algebraically, we can see that distance from U to V is the same as norm u minus v. Now that's the same as distance from u to minus v, so u minus v, which means u plus v. Okay. Now once that is assumed, then now we have to show u and v are orthogonal. Okay, that is assumption. Now then, even though you make a square, that will be the same. Okay, so from left hand side, if we expand, then that is now u norm squared plus v norm squared, and that is minus 2u dot v. And right hand side is the similarity, that is u norm squared plus v norm squared, and that is now plus 2 and u dot v. They're the same, and after canceling these two, and we can say that here now u dot v is 0, right? So from this assumption, we reach at u dot v is 0, which means u and v are orthogonal. For square matrix A, vectors in column space A are orthogonal to vectors in null space A. Okay. Earlier, we saw that there are some example so that a non-zero vector is both in column space of A and null space A, so that this statement is false. For on n by n matrix A, vectors in the null space of A are orthogonal to vectors in row space of A. Okay, that one is here one of the statement over there, so that is true. For now, that is null space of A and row space of A, but you should not be confused that there is a column space of A and that is here null space of A, so they are different. It is false and it is true. Okay. Okay, that's it. Thank you.